Hello everyone. In this video we are going to discuss about UniJunction transistor. Simply we call this as UJT. So a UJT is a three-terminal silicon semiconductor device which has one PN junction. This is the structure of a UJT. For this N-type semiconductor and a P-type region. So with a P and N region, a PN junction is formed. These are the basic construction of a UJT. This UJT, we can use this as an oscillator, but we can't use this UJT as a linear amplifier. It exhibits negative resistance characteristics. This negative resistance characteristic is used for using UJT as a oscillator. Moreover, UJT has the ability to control large AC power with a small signal. We can use UJT as a triggering device for triggering SCR triac. SCR triac are the power electronic devices because they are called power electronic devices because they can carry large amount of power. That's why we can say that UJT has the ability to control large AC power with a small signal. We using this UJT to trigger the SCR and triac. SCR and triac are the power electronic devices. This is the basic construction of a UJT. In its construction, an N-type semiconductor bar and a P region. A P region is formed on the N-type semiconductor bar. A PN junction is formed. Emitter terminal is taken from the P region and base terminals. There are two base terminals named as B2 and B1. Two base terminals are taken from two ends of the N-type region. And the second figure shows the symbol of a UJT, emitter and base 2 and base 1. It consists of a N-type silicon semiconductor bar and a P-type silicon region. N-type bar is called base and P-type region as emitter. PN junction is formed between emitter and base region. In the construction of UJT, emitter region is heavily doped while base region is lightly doped. Due to this reason, resistivity of base is very high because base region is lightly doped. Emitter terminals are taken from the emitter region and base terminals are taken from two ends of the base region. Three terminals are labeled as emitter, base 1 and base 2. And one more important point is emitter region is close to base 2 terminal than base 1. And this is the equivalent circuit of UJT. So a UJT circuit can be replaced by its equivalent circuit as shown in the figure. A PN junction is replaced by a diode and the N-type semiconductor bar has internal resistance. RB2 is the internal resistance between the emitter and base 2 region. RB1 is the internal resistance between the emitter and base 1 region. This total resistance RB2 plus RB1 is called interbase resistance and is represented by R subscript BB. RBB equal to RB2 plus RB1. This is the basic equivalent circuit of UJT. Here RB1 internal resistance is represented as a variable resistance because that resistance, the resistance between emitter and base 1 is variable. That's why in its equivalent circuit RB1 is represented as a variable resistor. When we are not applying any voltage at the input, that means the input is emitter region. When we apply no voltage at the input region, the internal resistance RBB varies from 5 ohm to 10 k ohm. RB1 is the variable resistance which is variable. RB1 varies with respect to IE. Depending upon IE, RB1 can vary typically from 4K ohm to 40 ohm. That means its internal resistance RB1 varies from higher value to lower value. Higher value means large voltage drop across RB1, and lower value low voltage drop occur across RB1. So the internal resistance RB1 varies from 4K ohm to 40 ohm. Next one is the intrinsic standoff ratio. Intrinsic standoff ratio is an important term related to the UJT. To explain the intrinsic standoff ratio, we have to consider the equivalent circuit of the UJT. For intrinsic standoff ratio, we have to apply an external supply voltage. Here we are going to apply the external supply voltage to B2 and B1. So when supply voltage is applied to the terminal B2, that means VBB is applied to B2. When we apply VBB to B2 and B1 is grounded, then emitter is open. VD is the voltage drop across diode. In this case, RB1 is a variable resistance that changes depending upon the conductivity occurring across that region. So we can take the voltage across RB1 as V1. So to find the voltage across R1, that is V1 equal to V1 is the voltage across RB1. So voltage across RB1 can be calculated by the resistance RB1 divided by, here the total resistance are RB2 plus RB1. So V1 equal to RB1 by RB2 plus RB1 into supply voltage VBB. So we can rewrite this as RB1 divided by RBB into VBB. Among this, RB1 by RBB is the intrinsic standoff ratio, which we can replace by a constant term eta. So we can write this as eta into VBB. So V1 is the voltage across RB1. V1 equal to eta into VBB. So intrinsic standoff ratio eta equal to RB1 divided by total resistance RBB. This is the intrinsic standoff ratio. The voltage drop across the resistance RB1 is called intrinsic standoff voltage. So V1 is the intrinsic standoff voltage. Let us move to the points of the intrinsic standoff ratio. Intrinsic resistance ratio RB1 by RBB is called intrinsic standoff ratio. The value of intrinsic standoff ratio is between 0.5 to 0.8. Voltage drop across RB1 is called intrinsic standoff voltage. We represent this as V1. This voltage reverse biases the emitter diode. So the function of intrinsic standoff voltage is it reverse biases the emitter diode. This is the UJT operation. To explain the UJT operation, we have to consider the supply voltage. So here we apply the input voltage VEE. We can give the input voltage as VEE. VEE at emitter terminal and VBB at output terminal. That means across B2 and B1. When we give the supply voltages, the voltage across RB1, that is eta VBB. Last we derive the intrinsic standoff voltage. So voltage across RB1 is eta VBB. This eta VBB and the voltage drop across diode is VD. So eta VBB plus VD. This voltage reverse biases the diode. Due to reverse biasing, the current flows through the diode is zero. That means the emitter current through the diode is zero. Emitter current through the diode is zero. When we increases the voltage when the emitter voltage increases to eta VBB plus VD, that time the diode become on or the UJT triggers or UJT become on. At that time the current starts flows. This voltage is called peak point voltage. The voltage at which the diode conduct is called peak point voltage. When the UJT reaches the peak point voltage, the diode become on, and in P region is the heavily doped P region. There more number of holes are seen in the P region. So when the diode become on, the holes moves from the higher concentration to lower concentration. In N region, holes are in low concentration, so holes move from P region to N region. And since the holes move from the P region to N region, the resistance RB1 decreases and the conductivity increases. Since the resistance decreases, the voltage across RB1 decreases. That means the diode become more forward biased. Here the voltage across RB1 decreases and then the diode become more forward bias. More forward bias means more holes are moved from the P region to N channel. This is a regenerative process, and this process is called conductivity modulation because this action happens accumulately. So we call this as a regenerative process. When the diode become on, the holes move from P region to N region and the resistance decreases, conductivity increases and the voltage drop decreases. Due to this, the more forward biasing occur at the emitter region. Due to the forward biasing, again more number of holes moves from the P region to N region, conductivity increases. That's why this process is called conductivity modulation, and this process repeated and repeated again and again. So we call this as a regenerative process. This is the working of the UJT operation. So in this, the resistance RB1 decreases and the current increases. When the resistance decreases, current increases. That portion is called negative resistance region, and that property is used to use this UJT as an oscillator. So let us move to the operation of a UJT. To explain the operation of a UJT, we have to apply the external voltages VEE and VBB. VEE is the external voltage applied at the emitter terminal and VBB is the voltage applied at the terminal B2 and B1. Emitter diode is reverse biased by a voltage drop across RB1 and its own barrier potential VD. Total reverse bias voltage across diode is equal to sum of eta VBB and VD. Diode remains reverse biased as long as the applied voltage is below total reverse voltage and emitter current equal to 0. When the emitter voltage equals eta VBB plus VD, diode conduct and IE flows, means emitter current flows. The emitter voltage at which diode conduct is called peak point voltage. Peak point voltage VP equal to eta VBB plus VD. At this condition, UJT is fired, triggered or turned on. At this instant, holes from P-type emitter region are injected into the base region. This reduces the resistance RB1, which in turn reduces the intrinsic standoff voltage. Intrinsic standoff voltage is the voltage drop across RB1 and increases the conductivity. This action is called conductivity modulation. This is a regenerative process because smaller value of intrinsic standoff voltage result in stronger forward bias and more holes are injected. As a result of this, emitter current increases. Next one is the VI characteristics of the UJT. In the VI characteristics of UJT, emitter voltage are represented on y-axis and emitter current on x-axis. In these VI characteristics, the characteristics are divided into three main regions. They are cutoff region, negative resistance region, and saturation region. When the emitter voltage is less than 0 up to peak value, up to Vp equal to eta VBB plus Vd, that times IE equal to 0. Here the IE is marked to the left of the 0 origin. So cutoff region is the region at which the emitter current is approximately equal to 0. And when the UJT reaches the peak point value Vp, when we increases the emitter voltage, that time the emitter current increases. When we increases the emitter voltage, the emitter voltage starts decreases and current increases. The emitter voltage decreases means the resistance in that portion decreases. We can see that in the working or UJT operation, the resistance across the N channel is decreases because of the increase in conductivity. That due to decrease in resistance, conductivity increases means emitter current increases. So here in negative resistance region, resistance decreases, voltage decreases, and emitter current increases. So up to a point, the resistance decreases. That point is called a value point, and when it reaches the value point, VV is the value point. When we reaches the value voltage, again its voltage started increasing. This is the VI characteristics of UJT. So the VI characteristics of UJT are classified into three main portions. They are cutoff region, negative resistance region, and saturation region. So cutoff region is the region to the left of the peak point, and in this region emitter voltage is below peak point voltage and emitter current is approximately 0. UJT is in its off position in this region. And next one is the negative resistance region. Region between peak point and value point is called negative resistance region. Emitter voltage decreases from peak voltage to peak point voltage to value voltage, and emitter current increases from peak current to IV. IP is the peak current and IV is the value current. The increase in IE is due to decrease in RB1. Because of this fact, this region is called negative resistance region. When UJT operate as oscillator, it is operate in this region. Next one is the saturation region. Region beyond the value point is called saturation region. Device is in its own position in this region. VE remains almost constant with the increasing IE. Next one is the applications of UJT. Applications of UJT are: we can use UJT as a triggering device for SCR and triac. Then next one is the non-sinusoidal oscillator. We can use UJT as non-sinusoidal oscillator, sawtooth generator, and a timing circuit. These are the applications of UJT. That's all in this video. Thank you.